In this video, we're going to be looking at a op-amp circuit configuration called an integrator. So I know that everybody's probably been having a lot of fun doing the circuit analysis, but you've been saying to yourself, you know what this is really missing? Some calculus. Well, don't worry, we're bringing calculus into the game now, so everybody can have that much more fun. So what we're going to see is we're able to do these more complicated operations by including the capacitor in the circuit. So let's quickly just analyze this. And so let's start with our ideal op-amp properties. So we know that we have zero current going into our ideal op-amp input terminals. So we have zero current coming in here and here. And we also know that the differential input voltage is zero. And so because our non-inverting terminal is at a potential of zero, then our voltage up here is going to be at zero as well. So I'm going to go ahead and put 0 volts. So we know that that is at what we call a virtual ground. So I can go ahead and label some other things as well to aid in my analysis. So let me define a current going through my resistor. And I'm going to define this as I sub R, and a voltage across my resistor, which I'm going to define as V sub R. I can do a similar thing for my capacitor. I'm going to define some current going through this capacitor as I sub C, and a voltage across it, V sub C. Notice in both cases I've defined it such that my reference current is going through a drop in our reference voltage polarity. That means we're going to use a positive sign in our passive sign convention, but there's no reason that you couldn't define voltages or currents differently. You just have to keep in mind that passive sign convention. Okay, so the basic approach is going to be the same as what we did for our simple cases where we only had resistors. So we're going to start with Kirchhoff's current law, KCL, and we're going to say we have IR going into that node, and we have IC also coming into that node, so plus IC, and then we have nothing leaving. Of course, we can rearrange that and say IR equals negative IC. So what we can do now is we want to use our IV equations. So let's just say from our IV equations, we can update this a little bit. So for our resistor, that's just going to be Ohm's law. So we can say VR divided by R is equal to our IR. For our capacitor, however, it's a little bit different. So remember, for a capacitor, we have I equals C dV dt. So this is our capacitor IV. And so I will point out to you that our capacitor is a passive element, so our passive sign convention is going to apply to our capacitor as well. And here is an equation that relates our voltage and current, so that means our passive sign convention is going to come into play here. Okay, so we have the negative sign, which we had out front anyway right here, so we're going to keep that negative sign, and then using that capacitor IV equation, we have that IC is equal to C dVC dt. So you can kind of see where that integration, that calculus is going to come from. Okay, so again, we said that we had an ideal op-amp, our differential input voltage is 0, so really we can say that VI is the same thing as VR. So we can update this and we can say VI divided by R on this side. And then similarly, we can say that our V output is the same as our VC. So I can update my right side of the equation and say this is C dV naught, or dV out, dt. Okay, so at this point, what we're going to want to do is separate and integrate. Okay, separate and integrate. And so what we get is we have dV naught on one side, and we have negative 1 over RC times VI dt. So what we get when we integrate, we'll have the integral from 0 to t of dV naught is equal to negative 1 over RC, that's a constant, so we can just pull that out front of our integral, is equal to the integral from 0 to t of VI of tau d tau, where tau is just a dummy variable that I've used because I have t in my limit, so I don't want to have t as a variable and t in my limits. So I've just used this tau as a dummy variable. So what we can do then is we do that integration. We get v naught of t minus v naught of 0 is equal to -1 over RC integral from 0 to t vi of tau d tau. And so typically we don't want to have to worry about this voltage at time 0. And so the way we can get around this is if we always discharge this capacitor before each use, then that voltage at time 0 is going to go to 0. So let's just say discharging cap before each use means that we have V out 0 should always be 0. So we're always starting with an initial value of 0. So then what we get is our output voltage is going to be a function of time, and it's going to equal -1 over RC times the integral from 0 to t of Vi of tau d tau. And so there's the expression that relates our output to our input. And so what we can see is our output is proportional to the integral of the input. So as promised, now everything has gotten a lot more fun, and we've introduced calculus. And like we said way back when we were introducing op amps, we said our op amps are capable of doing all of these operations, addition, subtraction, multiplication, all of this stuff. And so here we've seen a more complicated example with our integration.